numbers and their operations. A complex number is in the form of a plus bi, where a and b are real numbers, they're constants, and I is the imaginary number that represents the square root of -1. First thing we're going to do is we're going to graph the complex numbers. We're going to start with 3 plus 2i. On the horizontal axis on our graph represents the real numbers, and the vertical axis is the imaginary numbers. So to graph 3 plus 2i, we're going to go to the right, 3 units on the real axis, up 2 units on the imaginary axis, and plot our point right here. So here is 3 plus 2i. The second problem we have is -4 plus 6i. We're going to go to the left, -4 units. We're going to go up 6 units on the imaginary axis. Plot the point. There's -4 plus 6i. -5 minus 3i, we're going to go to the left 5 units on the real axis. We're going to go down 3 units on the imaginary axis. Plot the point. There's -5 minus 3i. And then the final point, 2 minus 4i, we have 2 units on the real axis to the right, down 4 units on the imaginary axis, and here's the point, 2 minus 4i. The first operation we're going to do with complex numbers is to find the absolute value of a complex number. To calculate the absolute value of a complex number, you're going to use the formula square root of a squared plus b squared. You might recognize this as the equation for the Pythagorean theorem. And the reason why we use the Pythagorean theorem is the absolute value of a complex number represents the distance the point is away from the origin. And we have a right triangle here. We're looking for the hypotenuse, and the hypotenuse, the length of the hypotenuse, you use the Pythagorean theorem to find. So to find the absolute value of -5 minus 3i, we plug in just the constants. We don't need the imaginary I. Square root of -5 squared plus -3 squared. -5 squared is 25, 3 squared is 9. We end up with a square root of 34. Here's another example, -4 plus 6i. Again, we're looking for the distance between the origin and the point. We use the Pythagorean theorem. We plug in -4 squared plus 6 squared. That's 16 plus 36, square root of 55. We can simplify the square root of 55 because 4 goes into, 52, not 55. 4 times 13 is the square root of 55. So we can pull, 52. We can pull a 2 out of the radical, end up with 2 square root of 13. The next operation we have are adding and subtracting complex numbers. In order to add and subtract complex numbers, you need to simplify any operations you have first, so we need to deal with the negative. We're going to distribute the negative into the second set of parentheses. So we have 5 minus 3i plus 2 minus 4i, and then here you're going to combine any like terms. We have real numbers and imaginary numbers. So you're going to do the real numbers first. 5 plus 2 to get 7. And then -3 minus 4. For the imaginary numbers, we end up with -7i. So again, you combine any real numbers together, and you combine any imaginary numbers together to get your final answer. Multiplying complex numbers. So first thing we need to do is FOIL. We're going to distribute all of the terms out. to get negative 4 minus 3i minus 8i minus 6i squared. We need to deal with I squared. I squared, we can rewrite this as the square root of negative 1 squared. And whenever you have a square and a square root, those two operations cancel each other out. So you're just left with the negative 1. I squared equals negative 1. So we can replace that in our equation. So after I substitute negative 1 in for I squared, I can combine any like terms I have. The negative 11i comes from negative 3i minus 8i. And negative 6 times negative 1 is 6, minus 4 is 2. So my final answer is 2 minus 11i. Complex conjugates. An example of a complex conjugate is a plus bi and a minus bi. Those are complex conjugates. And if you notice, the b is positive in one of the terms and the b is negative in the other term. So we're going to multiply these complex conjugates together. So we're going to distribute like we did last time, end up with 36 plus 12i minus 12i minus 4i squared. We are going to replace the I squared with negative 1 just like we did last time. And when we combine the i's, we have plus 12i minus 12i. Those guys cancel out. So we're left with 36 minus 4 times negative 1. That equals positive 40. Notice that the product of complex conjugates are real numbers. All of the i's canceled out. The I squared turned into negative 1, and then the two I terms were opposites of each other, so they canceled out. They will always be opposites of each other when you're using complex conjugates. So if you're multiplying those together, you should not end up with an imaginary number in your final answer. It should only be real numbers. The final operation we have are dividing complex numbers. So divide complex numbers. The rule is you're not allowed to have an imaginary number in the denominator. The only way to get rid of the imaginary number in the denominator is to multiply by the complex conjugate of the denominator. The reason why we multiply by the complex conjugate of the denominator is to get rid of all of the I values. Be very careful when you distribute. You need to distribute on the top and the bottom. Be careful when you're foiling out. We end up with 2 plus 3i plus 8i plus 12i squared in the numerator. And in the denominator, we have 1 plus 4i minus 4i minus 16i squared. Replace any I squared values with the number negative 1. And then you're going to combine any like terms. 2 minus 12 is negative 10. Positive 3i plus 8i is 11i. The i's in the denominator, 4i minus 4i, cancel out, and we're just left with 1 minus 16 times negative 1, which is 17. What you're going to do now is you're going to simplify the following problems. So you're going to use the skills that you just watched. You're going to simplify the absolute value problem, the multiplication problem, and the division problem. Once you find your answers, you're going to show me your solutions. Make sure you show it to me before the end of class.